I'm Amanda Graham. I am the academic director for the Irving Institute for Energy and Society at Dartmouth College, and I am really pleased to be bringing you a supplemental session on learning the language of energy. My background is actually in communication studies, and so for me, this is where the exciting stuff about energy comes together with language and communication and becomes really powerful tool and as a sort of entry key into being able to get into a community. And so learning the language of energy is a tremendously important part of being able to get fluent in and know how to navigate making decisions, making choices about energy, both for yourself and for society writ large. So we're going to have two parts to today's session. And the first part is going to be navigating the ocean of concepts and laws. But as we even start to get started there, sometimes when you think about units and laws and energy, you look for resources, you find something like this, which is a fantastic resource actually that was created by graduate students at MIT in the mid 2000s. There's a ton of information here and it's really incredibly useful. But sometimes what happens to us is we get overwhelmed with that information. And it's just too hard to digest. And so what we're going to try to do in this session, actually, is equip you with a compass to help you to navigate through these oceans, a North Star to look up to as you're navigating, and with the vocabulary to help you move along in the mix. And so that compass is our key concepts of energy. Your North Star is the first and second laws of thermodynamics, and then your vocabulary are those key energy units that we'll work with. And we're going to do all of this in the context of the Lawrence Livermore National Labs Sankey diagram that we're working with in our Energy 101 series really closely. So let's go ahead and get started with the very most basic concept and term, energy. What does energy mean? The term of energy means, from a physics standpoint, the capacity to do work, right? So we can talk about energy consumption, we can talk about energy use, and we also often talk about energy that we may waste. And when we're thinking about energy as the capacity to do work, it's helpful to distinguish between potential energy, which is energy that's stored. So like this gallon of gasoline, or even the energy stored in this apple, versus the kinetic energy, which is energy in motion. So energy that is actually doing something, doing that work, propelling that bicycle or turning that wind turbine. And so if we go back to our Sankey diagram, we can see over here on the far left, all of these sources of energy are different potential forms of energy. So the potential energy in the sun, the potential energy in the wind, the potential energy in our unit of natural gas or coal or petroleum. Even our electricity, right, that's generated from those original sources of energy is a potential form of energy because it has not done the work yet. But then when you get over to the sectors that we use energy in here in the United States, we look at these different sectors of residential energy use, commercial, industrial, and transportation energy use. That's where we're looking at kinetic energy, energy that's in motion that is actually doing work. And that slide also showed an important distinction between primary energy sources, so the solar energy, the wind energy, the petroleum, and the secondary energy. So electricity is a great example of a secondary energy source. We have to make electricity from something. You have to burn a fuel in order to, or capture a fuel like wind or solar in order to have a secondary source, something like electricity. Hydrogen is often another example of a secondary energy source. And that's important because when we think about using more and more electricity, what matters is not just that we're using electricity, how is that electricity being made? Where is it coming from is also a critical question for us to ask. So here again, just showing that relationship between the primary energy and the secondary energy as we're seeing here on the Sankey diagram. So another distinction that's important to make is between energy as a quantity, something that we can measure as it's being used, is different from power. often the terms of energy and power are used interchangeably, but actually power here is an instantaneous rate of use, right? So it's how much use is my refrigerator consuming at a given moment in time. Here it's rated between 100 and 400 watts for this kind of a model, which means that over a period of time, so over the period of a year, it's using 400 to 100 kilowatt hours of energy. It's consuming that amount of energy over a year. So oftentimes we see our appliances and we can understand how they're rated for a given moment in time, but that doesn't tell us how much energy they actually use for an hour, a day, a year. And here what we're measuring on the Sankey diagram, we see this large measurement of energy consumption for the United States, the most recent Sankey diagram available at 100 quads, right? And a quad is a quadrillion BTUs. And we'll get more into that in the next special session where we talk about energy units. And so as we're looking at those energy sources along the left side of the Sankey diagram, we also recognize that energy density varies among energy sources. One of the reasons why we are so dependent on fossil fuels is that they are incredibly energy dense. And so within a certain unit of gasoline, there are 47 units of energy that can be expended, 47 megajoules of energy that can be put to use there, versus a comparable volume of wood that only contains 16 megajoules. And so you're gonna, with the same amount, the same volume of that energy fuel, you can do much more with a fuel that is energy dense than you can with a fuel that is much less dense. So that's a really important consideration for us as we're making our energy choices. And here, back again to the Sankey diagram, you see that the sources that are outlined in gray, those are relatively speaking, low energy density sources of energy, as opposed to the ones that are highlighted in red, which are high density sources. Being high density, in some cases, makes them really easy to transport, right? And easy to manage in ways that can be much more challenging for fuels that are less energy dense. And here's just a chart indicating the relative energy density of this number of this variety of energy sources, where you see that, you know, between solar energy and natural gas, there's a tremendous difference in many scales of magnitude in just how much energy you get out of a certain spatial allotment for that source. So now let's shift gears from some of those basic energy concepts to talk about thermodynamics. And a lot of people get scared at the word thermodynamics. And I'm here to say that there are two key things that you want to take away about thermodynamics, the first and second law. And they really, in practical terms, they're really important, and they're not to be intimidated by, right? So the first law is that energy cannot be created or destroyed. It can be transferred or moved and converted, but the universe has the amount of energy that it has. Second law of thermodynamics is that when we do that conversion or that transfer of energy from one source to another, from one form to another, there's always a loss. The more times that you convert that energy, so if you're burning a fuel and then turning a turbine, that the more times that you are manipulating that energy between the source and the use, the more losses you will have. And so what I would compact that into is to say, so that first law of thermodynamics is the conservation of energy, right? There is only a finite amount of energy available. But then that also comes along with this fact that there is no free lunch, right? You can't get something from nothing. You're always going to lose something when you're changing the form of energy before you actually use it. And so this is a little illustration of that, right? So you've got an apple, you know, which is a form of potential energy being consumed, then being converted into kinetic energy by our bicyclist. But if you see in my beautiful orange lines there, there's energy that's not being used to propel the bicycle forward, and it's being lost in the form of heat energy, right? And so not all of the apple's energy actually is going towards the propulsion of the bicycle forward, and that's a form of a conversion loss. And here in a more traditional example of that, you'll see what happens when we go from a power plant that is consuming a source of energy, burning a fuel, and 65% of that is lost as heat, you move that over into the transmission system for electricity, you're losing a chunk of that on the wires. And then when you turn your light bulb on, if you were to use an old-fashioned incandescent bulb, again, you're losing 95%. And so in the end, what you have is 5% of the energy that went into the power plant comes out as light. So that's an example of those losses that we see due to that second law of thermodynamics. And here, back to the big picture again with our Sankey diagram, what that translates into is a tremendous amount of wasted energy, that is not deployed for providing us the energy services that we need. And on the Sankey diagram, we recognize that as rejected energy. So what you'll see here is that fully two-thirds of the energy that comes into this country, that we use in this country, ends up being wasted, because only about 32.7 or 33% of it is actually going towards energy services and energy uses. And so one way to see that is as a tremendous waste, but another way to see it is as a tremendous opportunity for energy efficiency, increasing energy efficiency, or figuring out ways to capture that energy so that we can make better use of it and waste much less of it. So that concludes our quick delving into key concepts and laws in energy space. And the next session, if you choose to participate, is on the ocean of units and how can we navigate the ocean of energy units. Thank you so much. That'll do it for now.